Hi guys, this is lesson 6.2. It's called Substitution. In this lesson, we are going to solve our systems. Remember, systems are lines on the graph, and we're looking for where the lines cross. And in this case, we are going to learn how to solve them by a mathematical process called substitution. In this, what it's going to look like is we're going to have equations like this, and one of the equations needs to be solved for one of the variables. So y equals is perfect. It could be x equals, but this is perfect. What we're going to do is we're going to take this piece of information, since we know that y equals 2x plus 1. We actually know that 2x plus 1 is the same thing as y. So we're going to take this 2x plus 1 and we're going to plug it in instead of y in the second equation. So we'll work some of these examples coming up. We'll just buzz through the book example to show you kind of how this goes. So we take the 2x plus 1, we plug it into that second equation, we simplify things, and we solve for one variable. We can only solve for one variable at a time. We can solve for x or we can solve for y, but we can't solve for both of them in one equation at the same time. So once we know that x is -2, the next step is that we need to use one of our equations, and in this case they've chosen y equals 2x plus 1, and we need to plug that -2, because we know that x equals -2, we need to plug that in and then solve, and we know that y equals -3. And so we have the pair of numbers, the x and y coordinate, -2 and -3, that give us the answer to where our lines cross. Okay. In the second example, you can see that we don't have an equation solved for one of the variables. It says x plus 2y equals 6 and 3x minus 4y equals 28. And so what they're going to do is they're going to take this equation, x plus 2y equals 6, subtract 2y from both sides, and get x equals 6 minus 2y. So notice that we have x by itself. Since we have x by itself, we now know something that exactly equals x. 6 minus 2y is the same thing as x. So we can go to our other equation, and instead of x, we're going to write 6 minus 2y. Okay, all of that because x equals 6 minus 2y. They're the same thing, so we can substitute. That's why we're using this word substitute. So we plug that in. We're going to need to use the distributive property. We're going to have to do some algebra, but then we get to y equals -1, and we've solved one of the variables. Now we need to find out what x is. So we can take one of the equations. You can use either one. In this case, they've taken the x plus 2y equals 6, and we're going to plug in the -1 instead of y, and that way we can solve for x. We do the algebra, and we find out that x is 8. So we know that we have this 8 comma -1, because we always put the x and then the y, and that's the point where our two lines cross. All right, sometimes weird things happen, okay? If you solve a system of equations and the end result is something false, like 3 equals -2, that's a no solution. And if you remember that no solutions are when we have parallel lines and they never cross, we call that inconsistent. If the result is an identity, that means we get an always true statement, like 3 equals 3, like 3 equals 3, then there are an infinite number of solutions. That means we have the same line. That means one line is on top of the other line, and all real numbers will be solutions, everything that's on the line anyway. And this is consistent, and it is dependent. Okay, so here's an example of that. Use substitution to solve the system. We have y equals, that's perfect. Since we know what y equals 2x minus 4, we're going to take that 2x minus 4 and plug it in instead of y in the other equation. And so then they do the math, they use the distributive property and do some algebra, and I'll do an example for you in just a minute. But they come up with this statement, negative 12 equals negative 12. Well, that's true. And that's an identity. And so whenever we have that situation, there are an infinite number of solutions. That is a consistent and dependent system. All right. So I want to do an example here for you. Let's say I have all those nice examples, and I'm going to do number 1 for you, and I have y equals x plus 5, and I also have 3x plus y equals 25. Sometimes when you see systems, they have a nifty little bracket like this. This textbook doesn't seem to do that very often, but that would mean that this is a system. It means I have 2 lines, and I want to know where do they cross. All right, so this one is already set up the way we want it. Y is by itself, and y equals x plus 5. So what I'm going to do is I'm going to use the second equation, and I'm going to plug in x plus 5 instead of y. All right, so now I'm going to combine like terms. I know that 3x plus x is 4x. I'm going to subtract 5 from both sides. Now I'm going to divide by 4. And I have x equals 5. Okay, that's 1/2 of what I need to know, okay? So I take x equals 5, and I need to plug it into one of these equations. I like y equals x plus 5. It looks nice and simple. If I plug in x equals 5, I get y equals 5 plus 5, or y equals 10. So now I have both pieces of information. I can write this point like this, 5, 10, and I know that this is the point where the 2 lines cross on the graph. I didn't get an identity, and I didn't get an untrue statement. I actually got a point. So these are going to be good. All right, let's work another one. X minus y equals 1, and 3x equals 3y plus 3. This is number 5 on page 347. All right, so neither of my equations is solved for one of the variables. So because this one has less going on, I'm going, by that I mean there's not a lot of the 3's that there are in the second equation. I'm going to rearrange this one. And I could subtract x, but then I'd have minus y left on the left. So I'm going to just plus y on both sides and get x equals 1 plus y, or y plus 1. That's nice and simple, right? So now I know that x equals this, that they're the same thing. And so I'm going to take this, and I'm going to plug it into this equation where x is. That was just kind of weird, wasn't it? So let's go 3 times 1 plus y, that's instead of the x, equals 3y plus 3. Okay, we need to use the distributive property here. So we have 3 times 1 is 3, and we have 3 times y is 3y. Oh wow, look at this. I have the same thing on both sides of my equation, okay? If I continue trying to solve this, those just canceled. So now I'm going to go like this, and those just canceled, and I end up with 0 equals 0. Or truly, 3 plus 3y is the same thing as 3y plus 3. This is an identity. It means that there are infinitely many solutions. We called that consistent. We called that dependent. all that means that this is the, oh, go away. All that means is that these are the same line. It's two different ways of writing that. In fact, if we had taken 3x equals 3y plus 3, and we had divided everything by 3, we would get x equals y plus 1, which is actually the same thing as there, right there, that form of the equation. All right. I want you to be able to work one. So let me give you this. Let's do number 2. Number 2 says x equals y minus 2 and 4x plus y equals 2. So you can go ahead and work that. Pause the video and see if you can use substitution to solve this. All right, x equals y minus 2. And so I'm going to take this y minus 2 and I'm going to plug it in the other equation for x. So now I have this 4 times y minus 2, because that's the same thing as x, equal, let's see, 4 times y minus 2 plus y equals 2. I need to use the distributive property. 4y minus 8 plus y equals 2. So 4y plus 1y gives me 5y. And then I'm going to add 8 to both sides. I'm going to divide by 5. I get y equals 2. Now, that's only half of my information. I need to also know what x is. So whatever you want to do, pick one of these equations. If I know that y equals 2 and I say x equals y minus 2, then I'm going to say x equals 2 minus 2, which is 0. X equals 0. If I had chosen the other one, that would be fine. I would say 4x plus 2 equals 2. And then I would work to solve this. I would get 4x equals 0. Divide by 4. Remember, dividing by 4 is fine. We just can't divide by 0. X is 0. So x is 0 in both equations. That's great. And so my answer is 0, 2. Always put them in alphabetical order. X comes first. X is 0 and y is 2. All right, I want to go back up and summarize this just a little bit. Okay, what is a system? They're just lines on a graph, and we're looking for where they cross. What did we already know before we did this? We knew how to solve systems by graphing them, by looking at the graph and seeing where the lines cross. What did we learn today? We learned how to solve the systems by substitution. So what we did was we solved one equation for one variable. So we need to get a y equals something or an x equals something, okay? And then we had something, I'm using the word something a lot, to substitute in for that variable in the other equation. We solved and we then knew what one of the variables was. We either got x or we got y. We take that and we plug it into the equation to solve for the other variable. Don't forget to solve for both variables. Some people forget and they only get x, only get y, but the answer or solution to a system is a point where the lines cross. So we need x and y because we need the coordinates for that point. I'm going to go here to the real world example now. A music store sold a total of 125 car stereo systems and speakers in 1 week. The stereo system sold for $104.95, and the speakers sold for $18.95. The sales from the two items totaled $6,000. $1,926.75. How many of each item were sold? Okay, so we have two situations going here. We know that we have, let's say C is car stereos, right? And T is the number of speakers, and C is the car stereo systems. There are so many word problems that actually follow this pattern. We have the first situation, which is we know the total of things. Without even talking about dollars, we know the total of things. We've got C plus T equals 125. Okay, that's just one piece of information that we have. The other piece of information has the values of things in it. So we know that each car stereo was $104.95, so we're going to multiply that together to get our total that we made on car stereos. And we know that each of the speakers was $18.95, so we're going to multiply $18.95 times the number of speakers to find out how much money we made off of those. We're going to add those two chunks up and get this total amount that we sold. The thing that we don't know is how many car stereos there are and how many speakers. We know how many items. There were 125 items, but we don't know them apart. We need to be able to put this equation and this equation together. Okay, so look at what they decided to do. They solved this equation until it said C equals. So remember, that's not really solving. That was a bad word to use, but it's actually rearranging the furniture, right? We rearranged it so that it says C equals. So we know we have 125 minus T that we can plug in instead of C in our equation. So they did that right there. And then they had to use the distributive property. They had to combine like terms, make it a little nicer. They subtracted this big number, $13,118.75 from both sides. And they got this, and then they divided by -86, and they found out that T, the number of speakers sold, was 72. Well, now we need to find out how many car stereo systems there were. And so what they decided to do was to use the easier, it looks easier, it's a little simpler equation. You'll get the same answer from both equations, but they plugged in 72 in for T and solved for C, which was 53. So they took a really complicated situation, took two equations, combined them, and then got where those two lines cross on the graph, which actually tells us something, that there were 53 car stereo systems and 72 speakers. All right, so go ahead and work your practice problems in Alex, and we'll see if you have some questions.